let's see if we can figure out how much of a frequency change there is and which way it goes. So let's calculate T, the period between when the pressure peaks hit the ear, or the tympanic membrane, or the detector, or the receiver. So T is what we think of it as in waves. It's the period, the time between peaks of this wave. So now let's imagine then two peaks look like this. All right, peak, I'm going to call this A, approaching, B there, then clearly that is the wavelength in air, distance between the peaks. And now we have over here, and of course the wave is moving. So even though we talk about the receiver moving, the wave of course is moving forward. That's how it hits you with its different peaks. The ear is here. And we know what an ear likes to do is receive those peaks. And we count what is the time between the ear hearing those peaks, and that's frequency, and that's what the ear detects. So let's say then the ear is moving at, I'm going to call that VR, the velocity of the receptor, or the receiver, is like what it calls it in the book. Yeah, a little R, we'll say. And this, the velocity of the wave is just V. For sound, that's always 343 meters per second. Okay, so now here's what we're going to do. We're going to actually do this as a kinematics problem. Yes, physics builds. So the ear passes A at T equals 0. And what we want to get is delta T from A to B. What is the time, this period we're talking about, the period, what the ear hears, is just the time it takes for the ear to get from this peak to that peak. That's what we're going to calculate. So how do we do that as a kinematics problem? Well, basically, if the ear is here and it's not moving, we could wait for this peak moving at V to get there in delta T. But if the ear is moving, it'll cover some of the distance itself. So we're seeing how long does it take the velocity of the ear going this way and B going that way to come together and meet each other. But they have to cover a distance lambda. So we say V times this delta T. So this is the wave moving one way, and the ear is moving VR delta T. The velocity of the receiver delta T. Those together have to be lambda naught. We didn't do proper kinematics, right? We could have had them say, when do they meet? And one's going positive, one's going negative. As an initial, I'll say, well, okay, we're not doing it proper because we're doing sound now, okay? But anyway, you get the idea. They both had to cover this distance, lambda naught. So this one went a certain distance, this one went a certain distance. There you go. Okay, so then we said the period we're looking for is that delta T. So let's solve for that delta T. Here we go, big T equals delta T. So here, pull a delta T out, and you see that it is lambda naught, the wavelength in the air, over V, sound, the speed of sound in air, plus VR. Yes. This is so good. Now, we don't think about sound in terms of period. We think of it in terms of frequency in hertz. Okay, so we just got to flip this over. The frequency is 1 over the period. So that's the speed of sound in air plus the speed of the receiver over lambda naught. There we go. So that is the sound that you're going to hear. And you can already tell that the ear hears a higher sound because the F naught, the frequency it should be, would be V over lambda naught. But we're taking something even bigger, V plus VR over lambda naught. So we actually already have our answer right there. But we like to write it in terms of the original frequency. I like to write it as 1 plus something times the original, because that's just how we do it. Okay? So this formula is correct, but we like to, it's not how we do it. We like to do it differently. So let me give you then the more standard formula way. So let me think how to do it. So this is the frequency the receiver hears, right? And now I'm forgetting how I do this. Let's see. So it's 3 is that over that, and then I bring that. What do I do? That over that times F naught over V. V over V. Oh yeah, sorry. So the frequency the receiver hears is, we're going to say V plus VR, but instead of putting it over lambda naught, we write lambda naught in terms of F naught. Right, it's the original wave. Oh, that's from the previous word. The original wave, we would say, we don't worry about the ear, we would say V equals F naught lambda naught. So we just want to write this equation in terms of F naught. So we have a lambda naught here, so we say lambda naught is V over F naught. Lambda naught is V over F naught. Ah, yes. And the reason we like to write it that way is then you get to say the frequency the ear hears is, what is this? 1 plus VR over V times F naught. 1 plus velocity of the ear over V times F naught. So that is the Doppler shift for the approaching source. In the book, I believe this is written as F plus, because clearly you can see it goes up. It's F naught times 1 plus whatever speed the ear is moving, VR, over the speed of sound. So it's a teeny fraction of the speed of sound, which usually is, F naught doesn't go up very much. Are those trains going at the speed of sound? No. You hear the effect of the train because you can detect very small changes in frequency with your ear. Okay, so, but you don't hear it go up by a factor of 2 or anything like that. If you did, you should run because the train is way too fast. Okay, one more thing about this equation is you might say, now wait a minute, it's approaching. Do I put in negative VR? How does it work? No. This is all derived where we thought about directions already. You put in whatever the speed is. If this needs to be negative and it go down, that'll be a different formula. That'll be the receding source formula. And even then you don't put in a negative. You put in the speed, but there'll be a minus sign here. Or some other formula with a minus sign. All right, so that is that. Okay, so we're done with the moving receiver.